Hello everyone. Let's wait for a couple of minutes for others to join. Meanwhile, you can ask any doubt if you have. Okay, let's get started. So, welcome you all to the live session 4 on the course of Fundamental of Manufacturing Processes. So, let's start solving some questions based on the week 4 lectures. So, this is the first question. Please read the question and try to find out the answer of this question. So what I will do, I will create a poll. You can give your response in the polling section. Yes, I have launched the polls. Please try to give your response in the polling section. After that we will solve it together. Yes, I have received one response. Okay, I will wait for few more seconds for others to give your response. Then we shall start discussing. Okay, whoever have answered, it's correct. So let's let's try to understand what is being asked in the question. So here it is being asked that with increase in percentage of clay in molding sand, what will happen to the grain strength? So we know how mold is made. Mold is made by molding sand, then clay, then water or moisture. Sometimes some additives are also added for specific requirements. So when sand, when mold is made up of sand, then it should have some properties, and strength is one of the properties. So basically, uh, when mold gets prepared, then it should retain its shape. It should retain its shape, its size, as well as it should able to hold the molten metal which is being poured inside it. So how this strength is measured, or one can find out what is the strength of the molding sand, and specifically if we talk about green sand, green strength. Green strength means strength of mold with moisture or in the presence of moisture. So the standard way of measuring the grain strength is, suppose we prepare the uh, molding sand by adding sand, clay and water. It is here. Now the standard way of testing the grain strength is uh, basically one cylindrical specimen is prepared from the molding sand by compacting it, and I will talk about the specimen which is made based on the American Foundry Society or AFS standard. So according to AFS standard, the in the height of this cylindrical specimen should be the 50.8, as well as this diameter should also be it should also be the 50.8. And what we will do, now we keep this cylindrical specimen uh, in horizontal testing machine, or there we will what we will do, we will apply force, and we keep on increasing the force till it retains its shape, or after a certain value of force it will collapse, then and that will be called as a grain strength. And uh, since it is grain strength, therefore the specimen should contain the moisture, and the strength value which we get, it comes something like that, kg per centimeter square. Basically we will keep on increasing the force, and whatever the value of force we will get, and for the given area of the specimen we will get the strength. grain strength, which has units of kg per centimeter square or any equivalent units. So let's see what has been asked in the question. So it is asking about the grain strength by adding the clay. So I would like to discuss some of the factors which would affect the grain strength. So let's start discussing this. Basically, size of molding sand also affect the strength. If if size of sand it will increase, then what will happen to the strength? It will go down. And similarly, if shape of the sand will be the regular, then strength will again down, because if if shape of sand will be regular, then there will be less mechanical interlocking among them. Suppose we have very regular sand. Since shape is very irregular, then just by giving some very little force we can easily displace them, or we can deform its shape. But suppose that if shape is very irregular like that, then these particles will remain interlocked with each other very firmly, and it will be very difficult to deform just by giving a small force. For that, larger force is required. Therefore, if strength is if shape of molding sand is irregular, then strength will be higher, or the vice versa. If shape is regular, the strength will be lower. Also, strength of mold depends on the degree of the ramming. So this is the ramming process. Basically, the molding sand is compacted. This is the ramming tool. With the help of ramming tool, when sand is when we try to compact the sand with the help of the ramming tool, what we do, first we will put pattern, and then we try to put the all sands over the pattern, and then we will start ramming. So if ramming will be higher, then the degree of compaction will be higher and strength will also be higher. Let's start looking other factors like effect of the moisture. So if we suppose that we want to make a mold and we have only sand plus clay, we don't have any moisture, do we get any strength? They will be basically in the powdered form. Suppose that these are the sand, and in between we will have clay, and if we won't put any water or moisture, then what will happen? They both will remain as a powder form and they won't take any permanent shape. So in order to activate the bonding between the sand and clay, we have to keep the moisture. So when we add moisture, then if we make any shape of it, then it can retain its shape. So basically, if we keep on increasing the moisture, the strength of the whole mold will increase up to a certain degree. So like here, on the x-axis we are increasing the percentage of moisture, and on the y-axis the strength. We can see when we increase the moisture, then the strength is increasing, up to a certain strength. But what after that? If we add more water to that, then again the strength will start decreasing, and this mixture, sand, clay and moisture mixture, will it will become very loose and strength will again go down. Therefore, by increasing the percentage of moisture, first strength increases, then decreases. Then let's see what happens with by changing the percentage of the clay on the green strength of the mold. Since clay its function is to basically, percentage of clay increases the bonding between sand, and therefore the strength of the mold increases. But it's not like however whatever amount we want we will keep on adding and strength will keep on increasing forever. It won't happen. You can see from the graph shown here, if we keep on increasing the clay, let's say from 5%, and practically it has been seen that after 15% there is if we further add the clay, then we won't get any advantage in the terms of the strength. So basically after this point we can see the if we keep on increasing the percentage of clay, there is very negligible increase in the strength. So this is the trend, how the green strength increases with the addition of the clay. Initially it increases rapidly with the addition of the clay, but after a certain point it saturates. So let's start looking at the options. By increasing the percentage of clay in the molding cell, the grain strength, first option is first increases then decreases. We have seen this is not the case. First decreases then increases. No, it should be first increases then stabilizes. So that is the correct answer. And fourth one is the first decreases then stabilizes. No, it's not decreases, it should be increases. So third option is the correct answer for this first problem. So am I clear? If any of you have doubt, please ask me, or I should move with the next question. Okay, it seems it is clear to everyone. So let's move to the next question. Please read the question and try to understand what is being asked, and try to solve it by yourself, and try to give your response in the polling section, and after that we will discuss it together. I have launched the poll. You can give your response in the polling section. Okay, I have got the responses. So yeah, one of you are correct. Okay, then let's start discussing it together. So what is being asked in the question? Sprinkling of mold wash. So if you can remember from the lectures that for preparation of the mold there are several types of sands, uh, which is, which can be used, which is used, like facing sand, mold wash, baking sand, and parting sand. So all of have very different functions, but here in the questions it is the question is asking about the mold wash. If you can remember what was the mold wash, so mold wash was nothing but basically it is a powdered graphite or sea coal. uh, it is sometimes it's added with the water or alcohol. Basically what happens when mold, when we try to make a mold, what we will do, we have upper part of the mold and lower part of the mold. Here it is scope, it is called drag. What we will do, we will take the drag and we try to fill it with the sand, and meanwhile what we will do, we will keep our pattern. Mostly the pattern is also it it's split, it's it is divided into two parts. So what we did, we took the drag and we tried to put the sand inside the drag, and then we put the first half of pattern inside the drag, and after that what we will do, we will put another second half of pattern over it, and now we will bring the cope, and again we will start filling with the sand, and after that we will do ramming to compact the sand, and then we will remove the cope, and then we will remove the pattern also, and at the end what we are left with, we are left with basically a mold with cavity. But what happens if all of totally, if we see in this region, the mold wall is made up of facing sand, but facing sand sometimes the wall finish or the surface finish is not very good. So some walls will be have some local distortions like here, which I have shown drawn in the figure. Then if we pour the metal inside it and we will make a casting, then definitely it will going to have surface defects. So to avoid this, what we use, the mold wash. Mold wash is powdered graphite or sea coal. Basically they are very fine, they are very fine in shape. Sometimes they are just directly sprinkled on the walls of the mold, but sometimes they are added with the alcohol or water. Then with the help of some brush, we try to uh, we try to put the mold wash on the mold mold wash. And after applying the mold wash, the surface the inner surface of the mold becomes very smooth. So there are the two functions of the mold wash. First is to improve the surface roughness. Basically, they fill all the pores which are present on the mold walls. They fill, since they are very fine, so they fill all the pores. They improve the surface roughness improvement by filling pores of mold wall. This is the one function. And another one is, since now the surface becomes very smoother, and when we will try to pour molten metal inside this mold, then the interaction of molten metal with the molten wall, it will become very less. So now the these are the regions where the molten metal will interact with the mold walls. Since now the surface is very smooth, so interaction will become very less, and because of that, what will happen, the penetration issues, like if surface was not very smooth, then metal mold metal with basically this mold wall get penetrated inside the metal and casting will become defective. So penetration of molten metal inside mold wall decreases. And also when molten metal is poured inside the mold wall, then there are some reactions between the mold wall and metal happens, and because of the reactions, some gases are produced, harmful gases are produced, and that is the another cause of the gaseous defect. Basically, whenever the molten metal interacts with the mold wall, due to some reactions, gas evolution will happen, and that gas will entrap inside the molten metal as a gaseous defect. So the task of mold wall to reduce the degree of reaction between the molten metal and mold wall, to reduce the evolution of gases. So these are all the functions of the mold wash. Now let's try to look at what are the options we have. The first option is fine pores on the mold wall are filled. Yes, they are here, filling of pores. Since they are very fine, that's why they are able to fill the pores of the mold walls. So that is correct. Now the penetration of molten metal is increased in the mold sand. No, because of the mold wash, the penetration is reduced, not increased. That is wrong. Surface finish is increased. Yes, since the fine pores of the mold wall get filled, that's why the surface finish will also increased. The interaction of molten metal and mold is reduced, which decreases the evolution of harmful gases. Yes, in the last part we have discussed that this is correct, that because of the mold wash, the reaction between the molten metal and mold wall gets reduced, and that's why the harmful gases evolution suppressed, or it gets reduced. So what, let's try to look what is the correct answer. First, third, fourth. First, third, fourth. Okay, this one is the correct. So if I am clear to everyone, then we shall move to the next question, or if you have doubt, then you can ask me. Okay, it seems everyone has clarity about this question. Then let's move to the next question. Please read the question and try to give your answer in the polling section. Meanwhile, I will create the polls for this question. I have launched the polls. You can give your response in the polling section. Yes, I have received one response. I'm waiting for others. Okay, I have got the 3 responses. Okay, all of you have given the responses. So 2 of you are correct. So, okay, let's try to look it together. So it is being asked in the question here. It has been listed on few of the properties of the course, and basically specifically it is being asked about the core sand, the properties of the core sand. So let's try to discuss it together. How cores are made? Cores are basically made up of core sand plus some binder and plus some water or moisture. And if you can recall the lectures, what was the function of the cores? Cores were used to create internal features. For example, suppose that this is the mold. Then if we want to manufacture a component with internal hole, then we have to put a core inside the mold. So function of core was to create uh, to create the internal features or holes. So there are here we have write down here it is basically written few of the properties like refractoriness, collapsibility, friability, permeability. Let's try to look all of them one by one. Okay, refractoriness. So it is a property. It is the basically ability of the core sand to sustain high temperature. Okay, now it's came. Yes. So refractoriness is the property of the core sand which enables the cores to withstand with the high temperatures. And since our core here, suppose that it is the mold and molten material is poured inside the mold. Now the core is surrounded by the molten metals, and therefore the lots of heat transfer would happen inside the core from the molten metal. And if it is a very desirable property of the refractoriness, like it should withstand with this high temperatures. It should not deform its shape. It should not uh, get damaged because of the high temperature. So refractoriness is the very desirable property for the core. But if you see in the question whether it helps to breaking the core, no. It is a desirable property of the core, but this property doesn't helps the core to break. What happens when the whole metal gets solidified? Then our coal will remain inside the casting, and during the solidification, because of shrinkage, lots of compressive forces comes on the core, and if this core is not flexible enough, or it is not able to collapse during the shrinkage, then there is a possibility of shrinkage cavity or the cracks formation in the casting. Therefore it is very desirable property of the core that it should get collapse. And the property of and collapsibility is defined in such a way like that the ability of the core sand to get collapsed after casting solidified, because we have to remove this also. Once we get the casting after the solidification, then we have to remove this, so that our final component should look like this cavity we will get only after removing the core. Yes, any one of you have doubt? Okay, if you have doubt, you can unmute yourself and you can ask. So once we basically, to remove the core, we have to break the core. So core is removed by breaking the core material from the casting, breaking or collapsing. That's why it is very desired that the core should get collapsed. So yes, this is the desirable property with respect to the breaking of the cores after solidification of the casting. So second is correct. What is the friability? Friability is very similar to the collapsibility, but there is a small difference. Like in collapsibility, what happens? Suppose we have core, and after solidification, we just try to hammer from the outside, and suppose it gets break into two parts or three parts, and it yes, this is the casting, and this red one is the core. And after the solidification, we try to remove this thing, and suppose we just hammered a little, and it gets break into two parts or three parts, and it came down easily. It came out easily. Then we call it it is very collapsible. And but sometimes it doesn't happen that easily. In such cases, what we have to do? Suppose this was the casting, and inside this our core is left, and we are trying to remove the core. But all cores, just by hammering or giving some impact load, the core is not breaking into three parts, and it's not getting removed easily. Basically, what happens when we give some impact load, or we will try to hammer it, then only very small part is deformed, and it gets broken, and it's came out. So just by one the material is coming out. What happening here? Core, here basically what happens, core is being converted into the very small particles or crumbles. So now it is not has broken into 2-3 parts, whereas we have to remove it out just by one by one, by removing the crumbles of the core material. So finally the whole core will come out like this, whereas earlier it was just broken into the two parts, or let's say three parts, and it came out from the casting easily. But now we have to break it into very small parts, and those parts are called crumbles. So when the friability or crumbling, they are very similar, but very small differences there, but they both are related to the breaking of the core. That's why these two options are correct. And what happens to the third option? It is the permeability. Permeability is nothing but it is the ability of the core sand which allows the gases to pass through it. Yes, it is desirable property of core, but with respect to the breaking of the core, it is not a correct option. So let's see. Suppose we have a mold like this, and we have a core. here, and it is filled above molten metal. So when core comes in the contact of the molten metal, evolution of gas will happen, and now this gas has to be come out from the core material. Basically they have to come out from here, from here, but it should we tried if it is a if it core material has good permeability, then the gases will come out through this. But if it won't have very good permeability, then again the gases will go inside the molten metal and they will cause the gaseous effect. Therefore this is a desirable property, permeability, but it has nothing to do with the breaking of the core. Therefore we have only two correct options, collapsibility and friability. So which is the second and third? Yes, this one is the correct option. So I think I am clear to everyone. If any of you have doubt, please unmute yourself. You can ask me, and if it's clear to everyone, then we can move to the next question. Okay, this question is also related to the core. Please read it and try to think of what is being asked in the question and try to solve it. And meanwhile I will create the poll. You can give your response in the polling section. I have launched the poll. Please try to solve the question and you can give your response in the polling section. It's live now. I have got 3 responses, so I am waiting for others. Okay, let's wait for a few more seconds. If you are facing any difficulty to understand the question, you can ask me. Okay. Unfortunately I haven't received any correct response. Okay, let's try to look at together what is being asked in the question. So it is being asked, the core is subjected to more thermal loading. Here we have to understand that what is the thermal loading, and then the core is subjected to more thermal loading than mold walls because of. So it is being asked uh, that in during the casting, when molten metal is poured inside the cavity, then there is a more thermal load on the core with respect to the thermal load on the mold walls. So here we have a schematic. This is the core, and these are the regions of the mold walls. Now when molten metal is poured inside the cavity, this whole region is the cavity region. When molten metal is poured inside it, then it comes into the contact of the core as well as the mold walls. So for this wall, this comes to the molten metal, and this comes in the contact of the molten metal from one side. The molten metal is coming to the contact of the mold walls from the one side, like this wall is coming from the it comes into the contact from the this side. Whereas for the mold, this whole mold is submerged inside the molten material. So if we look it in the 3D, so it has been surrounded by the molten metal from all sides. Whereas if we suppose that if we want to make a schematic of mold walls in 3D, I should make it a little simpler. Suppose this is now the molten metal is poured here. Now if we take this right wall, this is the right wall of the mold. Now this right wall coming to the contact of the molten metal only one side. And now what will happen? Heat transfer will take place from the molten metal to the right side of the wall from the one side. But whereas the core, which is surrounded by the molten metal from the all sides. So what will happen? The heat will try to enter from the molten metal. Well, I will draw molten metal also. Now heat will try to enter the core from all sides. Here, from there. So from all sides the heat will enter from the molten metal to the core material. So that is the reason why the thermal loading on the core wall is higher in comparison to the mold walls. Mold walls are exposed to the molten metal from the one side, whereas the core is exposed to the molten metal from all sides. So that is the reason. Uh, that is the reason why the thermal loading on the core material is higher with respect to the mold walls. Let's see which option is correct. First one is the core shares more surface area with molten metal to absorb the heat from it. Yes, it is correct because it is surrounded by all sides from the molten metal, so more area of the core material is coming in the contact of the molten metal, and that's why it has higher thermal loading. So first this is the correct. Let's see other options. Core shares the less surface area. No, it should be more, so that is wrong. Core has less density than molten metal. This option is correct with respect to the mechanical loading, not with respect to the thermal loading. Okay, let's try to explain what is the mechanical loading. When core material is like here, the whole core material is inside the molten metal, and usually what happens, core has less density. It has less density than molten metal. And we know, if according to the if we have read it, fluid mechanics, there we have Archimedes principle, like basically, since the core material has less density, then it will feel an upward force inside the molten metal. So basically, what the force which is it experiences because of density difference inside the molten metal, so that is called the mechanical loading. Whereas the heat transfer which happens from the molten material to the core material, that is called the thermal loading. So mechanical loading has to deal with the forces which acts on the core, which it remains when molten, it remains inside the molten material. So that is called the mechanical loading. So core has less density, it is correct, but the thing is, it has nothing to do with the thermal loading. That's why this option is wrong, but this statement is correct. Now let's see the fourth option. Core has more density than that of molten metal. No, it's usually, it doesn't happens like that. Most of the times, or the all we can say always, the density of the core material is less than the molten metal. So fourth one is also wrong answer. So only correct option is okay, the first one. So there are basically, whenever the core placed inside the molten metal, two types of loading are there: thermal loading and mechanical loading. Thermal loading happens because of the heat transfer from the molten material to the core material, and mechanical loading happens because of the density difference of the core material with the molten material. So here in this question, only thermal loading part has been asked. So I think I am clear to everyone, but even if any of you have doubt, please unmute yourself and ask. Okay, it seems it is clear to everyone. Then let's move to the next question. Yes, this question is related to the basically mechanical loading of the core. So please read it and try to give your answer in the polling section. Meanwhile, I will create the poll, and any of you feel any doubt anywhere, then uh, please stop me, and we can discuss it together. And if it's clear to everyone, then we shall keep on moving. So I am creating the poll for this question. Please take some time. Please try to solve and calculate, and try to give your response in the polling section. After that, we will solve it together. I have launched the polls. You can take your time to calculate, and then you can give your response in the polling section. And if you have any difficulty in understanding the question, you can ask me. Okay, I have got couple of responses. I am waiting for others. Okay, I think I have received all responses. Yes, two of you are correct. Okay, let's try to see together how to solve this question. So, what information are given in this question? First one is the density of the zinc liquid metal, and the density of the sand core. These are given. So we will list it down what are given. So I am using symbol rho for the density. So density of zinc is given 0.07 Newton per centimeter cube, and then density of the core sand is given 0.015 Newton per centimeter cube, and volume of the core, it is given V core 200 centimeter cube. Now it is being asked the magnitude of buoyancy force on the core will be. So what I will just quickly explain the how buoyancy force acts. So for that I will take an schematic. Suppose we have molten metal and we have a core material. Let's say core has some square shape. So whole core is surrounded by this molten metal, and suppose since it has raw zinc and it has density of raw sand, if this if this both density would have been equal, then it would haven't experienced any force, but now it is experiencing a force because of density difference. What happens, any fluid had tendency to apply a force equals to which is equals to the basically every fluid has tendency to apply a force which is equal to the weight of the fluid which is being removed. So suppose this is volume V. Now when this volume V of core has been completely submerged inside the molten metal, then it would have removed the same amount of molten metal inside in this region. And now what will happen, since all fluids have tendency to apply a force which is equal to the weight of the removed material, and the direction of that force is upwards, and that force will be equals to the weight of the removed liquid, that is equals to the volume into rho into G. Whereas there is another force which would have been acting on this block because of its own weight, and that will be equals to volume of the core multiplied by density of the core, which is raw sand, multiplied by the G. So if raw sand will equals to the row of molten metal, then it won't experience any force. But if there will be difference in the density, then the core will experience a force, and which will be equals to what? Volume of the core multiplied by the density of the difference in the density of the both material. Basically here density of zinc minus density of the sand. And let's try to, so I will call it F buoyancy. So we will try to put the values here. minus the raw sand, which is equals to 5 Newton per centimeter cube, which will be equals to 200 centimeter cube multiplied by 0.055 Newton per centimeter cube. Now if we solve it, we will get 11 newtons. So the F buoyancy, force of buoyancy on the core will be 11 Newton. So third one is the correct option. I hope I am clear to everyone, but still if any of you have any doubt, please unmute yourself. You can ask any doubt if you have, and if it is clear to everyone, then we shall move to the next question. Okay, it seems I am clear to everyone, so let's start looking at the next question. Please read the question, try to understand, and try to solve it by yourself, and try to give your response in the polling section. Meanwhile, I will create the poll, and after that we will solve it together. Yes, I have launched the polls. You can give your response in the polling section. Okay, I have received couple of responses. Okay, let's start discussing it together. It is being asked the features of bottom getting system. If you can remember, uh, basically there are two types of getting system through which we try to pour the molten material inside the mold cavity. So I will quickly draw schematics. So this is the schematic of top getting system. And there is another way. Okay. Suppose if we have mold cavity and here this is the example of bottom gating system. There are others also like parting line gating system or stepped gating system, but uh, if we can understand these two, then it will be sufficient for this answer, for this question. So what happens, we will try to pour molten metal inside the cavity. Here the cavity is open. Here this is the cavity region, and here this is the cavity region, and our aim is to fill the whole cavity region with the molten metal. So molten metal is being poured, and it will come in bottom gating system. The molten metal will enter inside the mold cavity from this bottom region, and whereas in the top gating system the molten metal enters inside the cavity from the top. Let's start looking together what will happen when molten metal is poured inside the cavity. In top gating system, when molten metal comes from top to the bottom, then its velocity increases, and because of this increased velocity the molten metal has some momentum, and when it will fall on this bottom of the cavity, then there is a possibility that it will erode the cavity walls, or some material inside the cavity wall gets removed, because molten metal is directly falling on the bottom of the cavity walls. So because of the impact or transfer of momentum, there is possibility that the molten wall get eroded. But where is in the what happens in the top in the bottom gating system? We are pouring the metal and it's coming down slowly and gently, it's entering inside the mold cavity from the bottom. Here it is not falling on directly on the any of the mold wall, it is coming slowly and then try to fill the whole mold. So there is very less possibility or very negligible chances of eroding the erosion of the mold wall. So first option, it says bottom gating system includes less erosion. Yes, it is correct, and we have already seen why it is true. Let's see the turbulence and splashing. In top gating system, when molten metal falls, when it falls on the mold wall, because of increased momentum and velocity, there is chances that molten metal will splash, or flow will not be flow will not remain a straight line or uniform. It there is possibility that some region of turbulence can happen, because it is not constrained. Whereas when flow here, when we try to pour the molten metal in the bottom gating system, then all times the whole pouring channel, like here is sprue pouring basin or sprue base, so all it is always filled with the molten metal, so there is no chance for the turbulence or splashing to happen. So molten metal will come uniformly gently inside the molten cavity. So yes, second option is also correct. Less possibility of turbulence and splashing in bottom gating system. Less aspiration problem. So what is the aspiration problem? What happens when we pour molten metal from top to the bottom, then velocity starts increasing. Now I will draw another schematics. Suppose this is the mold walls and we are pouring molten material inside the mold. Since velocity of molten metal keeps on increasing, and therefore area of cross section of the flow will keep on reducing as the velocity of the molten metal keeps on increasing. So initially whole molten material, the stream of molten metal, it was covering the whole width of opening of the this pouring basin or the opening of the mold. But when velocity increases, because area of cross section of the stream reduces, there is separation of the molten metal stream and mold wall. Since velocity increased, the stream becomes narrower and it gets separated from the mold wall. Also, in this region, a low pressure area has been formed. Basically, where the separation of flow happens, that is also a low pressure region, and because of that there are some small pores inside the mold. And before pouring the molten metal, lots atmospheric gases, and they were sitting inside these pores. So all the gases like nitrogen, oxygen, hydrogen, all the gases from the atmosphere, they were already found some space in the mold wall, in the pores of the mold wall. But when low pressure region will form, then what will happen? Then these gases which were sitting inside the pores of the mold wall, they came outside and they will try to diffuse inside the molten metal. And we don't desire this. We always want our molten metal should be free from gaseous defects or gaseous inclusions, because they will otherwise they will form blowholes. So we don't want these gases to come in the contact of the molten metal, but because of separation of the molten metal streamline, low pressure and formation of the low pressure region, the gases which were already present inside the pores of the mold wall, they came outside and they got dissolved in the molten metal. This is called the aspiration problem. So basically, aspiration problem happens because of this separation of the molten metal from the mold wall. Now this aspiration problem can be tackled in the bottom getting system by reducing the cross section area of sprue from top to the bottom. Basically we are tapering the cross section area of the sprue, since we already know when then the molten metal will come down, its stream will get narrowed because of increase in velocity. So a priori we are designing the sprue in such a way that there should not be separation of the mold wall. If we avoid the separation of the mold wall from molten material, then there will be no low pressure region formation will take place, and no gas from the mold wall will diffuse inside the molten metal. So in bottom getting system we can avoid this thing, the aspiration problem. But what we can do inside the top getting system, we don't have any option, because from molten metal will come directly inside the cavity, and in cavity region, this region will be the open, and since this region are open, then low pressure region formation will take place, and again the gases which are present inside the cavity, they will diffuse. So this problem cannot be avoided in the top getting system. So in this question, for bottom getting system, less aspiration problem, this is correct. Let's look at the last option, filling time. Here in top getting system, the metal was coming directly inside the mold cavity, and since it is coming directly inside the mold cavity, that's why filling will become faster. It will take very less time to fill the mold. Whereas in the top getting system, the molten metal has to travel from the sprue to the sprue base to the runner, and then it has to enter the mold. Since it has to travel larger distance inside the bottom getting system to reach the mold cavity, so molten metal has to travel larger distance to reach the mold in the bottom getting system. That's why it will take longer time to fill the mold. Longer mold filling time. So last option is not correct. It will be large, the filling time will be larger, not the smaller. So it will be a wrong option. So only correct statements are first, second and third. So which is the correct option here? So first one is the correct option, correct answer for this question. So any of you have doubt, you can ask me, or I shall move to the next question. Okay, it seems it's clear to everyone. Then we will move to the next question. Please read the question. Yeah, it's straightforward from the lecture. So I will try to create the poll, and please you keep your responses in the polling section. After that we will solve it together. I have launched a poll. Please give your response in the polling section. Okay, I have received couple of responses and one of you are correct. Okay, let's try to discuss it together. It is being asked, ability of sand to sustain high temperature of the molten metal is called. So option is grain strength, dry strength, hot strength, ultimate strength. So let's try to look the definition of each one by one. So grain strength is the strength of mold when it has moisture. If all of you can remember, then mold is made up of sand plus clay plus moisture or water, and sometimes some additives are also added to get some specific properties. So these are all the components of the mold. So grain strength is defined the strength of the mold when it has moisture. When it is the strength of freshly prepared mold. We mix all of them and we try to make a mold. So let's here I have just I have drawn just a rough schematic of a mold. This is the very freshly prepared mold. So this the molding sand, this is the reason where the mixture of sand plus clay plus moisture plus additives all has been added. So when it get prepared freshly, then whatever the strength it has, it is called the grain strength. So everything is present: sand, clay, moisture, additive. So in the presence of moisture, whatever strength it has, so it is called the grain strength. And grain strength helps to maintain the shape and size of the mold. It is a strength of freshly prepared mold. Basically, because of grain strength, the mold can maintain its shape, size initially. So suppose when we prepare the mold and somehow some disturbance would come, like some it's get hit by someone or something, so it should not get break. So there is, because of this grain strength, because of smaller disturbances or smaller forces, the mold is able to maintain its shape and size, and that is called the grain strength. And what happens with the dry strength? Okay, I have to remove this. Sometime when the casting size is very larger, then we cannot directly pour the molten material in the grain mold, because grain mold have a very less strength to hold the uh, load of the larger amount of the molten material. If casting size is smaller, then it's okay, we can directly prepare a fresh mold and we can pour molten material directly inside the mold. So grain strength will be sufficient to hold the molten metal as well as to retain the shape and size of the mold. But sometimes when the size of casting is very large, then grain strength is not sufficient to bear the load of the molten metal, because it because large amount of molten material has to be poured to produce the casting. So what we do, we take the, like earlier we had this grain mold. We try to improve the strength of the grain mold by drying it or by removing the moisture, and the strength which we get after baking or removing the moisture from the mold, that is called dry strength. So what we do, we take the mold, this is the mold, and we put it inside a furnace. Suppose it is an electric furnace, and we maintain the temperature in between 150 to 350 degrees Celsius, and we bake it for 8 to 48 hours. So what happens, the water molecules which is present inside the grain mold, it gets removed. So water molecules comes out, and the bonding between the sand and clay, that will becomes stronger, and overall strength of this mold gets increased. And since its strength is increased, then now it is capable of holding larger amount of, or the larger weight of the molten metal without being without any distortion. It can retains its shape as well as the size. So dry strength is the strength when this dry strength is the strength of the mold when there is no moisture. So that is called the dry strength. But what is the hot strength? Hot strength is the strength of the mold wall at the temperature of the molten metal. When it happens, suppose we have a mold cavity like this, and now we are pouring some molten metal inside this cavity. And these are the mold walls. Whenever we pour the molten material inside this cavity, then the molten material will interact with these molten and these mold walls. And because of heat transfer will take from molten metal to mold walls very quickly, then there is a skin of region, or the small region of the mold wall. This region has temperature very similar to the temperature of the molten metal. Temperature of mold walls will be roughly equals to the temperature of molten metal. Now when earlier in the dry strength, the temperature range which we have dried it 150 to 350, but the molten metal has temperature, uh, suppose if it is steel, then that its temperature will be greater than the 1500 degrees Celsius, or if it's aluminum, then it's have temperature greater than 660 degrees Celsius. So this temperature is very high than what we have used for the drying the green mold. So that strength the strength of the mold at the temperature of the molten metal, so that strength is known as the hot strength, and that strength is very much desirable at the time of the pouring of the molten metal, because when molten metal will come inside the mold, then mold should retain its shape and size, its dimension, without getting disturbed, in order to make the desirable casting. So its hot strength is very much required. So this is the definition of the hot strength of mold wall and the temperature of the molten metal. So as per the question, the ability of the sand to sustain high temperature of molten metal. So when molten metal comes in the contact of the mold, then hot strength is going to come into the picture. So if it has good hot strength, then it will sustain its shape and size, and we will get a very good casting. So for this question, hot strength is the correct answer. So okay, I think this question is clear to everyone, or if any of you have doubt, please ask me. Okay, I think it's clear to everyone. Then we shall move to the next question. This question is about the riser. So please read it and try to find out which are all the correct statements, and you can give your response in the polling section. Meanwhile, I will create the polls. Yes, polls for question 8 is live now. You can give your response in the polling section. Okay, I have received couple of responses. Okay, let's try to solve it together. What is the in the question? It is being asked what is the function of the basically what are the function of the riser. So if you can remember, then we can quickly make a diagram. This is the schematic of the casting. So from here we try to pour the molten metal. This is the pouring basin. This is the sprue. This is the gate. This is the cavity, and this is the riser. When we try to pour the molten metal inside the cavity, there are certain things which we keep in our mind. Like first thing is the whole cavity should get filled. So we should put we should pour sufficient amount of molten metal to fill the cavity. Then we leave it for the solidification and cooling down of the casting. So whenever the solidification process happens, then there is a shrinkage of volume of molten metal will take place. So if you can remember, then let's say we are drawing the graph for the eutectic alloy or pure metal. So this is a temperature time plot. This is the temperature of the molten metal. And now when we pour, it is the temperature during the pouring. And now the temperature will start decreasing and it will reach to the solidification temperature or melting point. This is the temperature where the metal starts solidifying, and this is the point where starting point of the solidification, and this is the ending point of the solidification. And after it we leave the casting to come down to this is the room temperature. So during the whole process, the volume of the molten metal keeps on decreasing during the whole melting process, as well as the here during the solidification process also. Here to here, when the temperature of molten metal will come to the melting temperature, this was the pouring temperature which was higher than the melting temperature, and this is called the superheat. So the temperature falls down from the molten metal temperature to solidification temperature, then molten metal starts converting into the solid, and then solid temperatures fall down to room temperature. This is the overall temperature time curve. So during the whole process, the shrinkage of volume take place. So from here to here there will be some reduction in the volume, and when the liquid metal transform into the solid, then again volumetric shrinkage takes place, and when it gets solidified and its temperature keeps on coming down to the room temperature, then also its volume keeps on changing. So we compensate these volumetric shrinkage with the help of riser. So from here to the molten metal temperature to the end of the solidification, this volumetric shrinkage is compensated by the riser, whereas the shrinkage which happens during the cooling of the solid metal is taken care by the pattern allowances. So what we do when we try to pour the molten metal inside the cavity, then we make a riser. Basically it is a reservoir where the molten metal gets collected, and the function of riser is to supply the molten metal when solidification process will start. So when solidification process start, then what happen, then some amount of shrinkage from all side will happen, and if we don't supply this metal, then the size of casting will reduce. But if since we have molten metal inside the riser, so that will come to the all the regions wherever the shrinkage is happening, and this process will keep on happening till the solidification process ends. So the function of riser is to supply the molten metal throughout the solidification process. So let's start looking at the options which we have to achieve the directional solidification. Yes, there is a term called directional solidification. In any casting, our aim is to fill the whole cavity from the molten metal, and for that what we want that molten metal should reach to the remotest place first. So in the whole cavity region, here we can see this is the remotest place. So basically this region is away from the riser, this is away from the riser, as well as this is away from the in gate. So our aim is to first molten metal should reach this region, and then solidification should start from here, and slowly whole metal gets solidify. So this process is called the directional solidification. We want the remotest place, solidification should start from the remotest place, and it should end at the places where either near the in gate or near the riser. So this process is called the solidification, because when solidification will keeps on progressing, then whatever the shrinkage will happen in this region, the molten metal will come from riser to or in gate inside the cavity. So if the remotest place, if the remotest area of the cavity will be solidified, will get solidified in very good way, then there will not be any shrinkage defects. So shrinkage defects can be avoided by the directional solidification process, and riser helps to achieve the directional solidification by continuously supplying the molten metal to the regions wherever the solidification is not has been happened. And our aim is to the solidification process should start from the here remotest place, and it should end near the riser and near the gates. So the molten metal inside the riser should get solidified in the last, and the molten metal which is far away from the riser, it should solidify first. So that is called the directional solidification. So riser helps in directional solidification. First one is the correct. Second is to compensate liquid to solid phase transformation shrinkage. Yes, already we have discussed. This is the reason. This is the reason where the transformation from liquid phase to solid phase happens, and here the change of volume or the shrinkage of volume of the molten metal will happen, and during this reason the riser is supposed to supply the required metal to compensate the shrinkage. So that is the correct option. Now third option is to distribute alloying elements in the casting. So riser has nothing to do with the distribution of the alloying elements. So this option is wrong, because alloying elements cannot be controlled, or distribution of the alloying elements, it has nothing to do with the riser. So whatever the elements will remain present inside the molten metal inside the riser, it will go throughout the cavity wherever the shrinkage will happen. But riser cannot control that this element should go there, this element should go another place. So riser cannot control it. That's why the third option is wrong. Fourth one is the to fill the molten metal to mold cavity. Yes, in fact another name of riser is to feeder, because it feeds the molten metal to the cavity during the solidification process. Therefore it is also known as the feeder. So fourth option is also correct. So for this question, statement 1, statement 2 and statement 4 are correct. Statement 1, statement 2, statement 4, okay. Okay, this one is the correct answer for this question. So I think I have explained the question. If any of you have any doubt, please ask me. Okay, it looks like that it is clear to everyone. Then quickly let's move to the next question. This question is all about the directional solidification. Please read it and try to get the answer. You can give your answer in the polling section. Meanwhile, I will create the polls for all of you. I have launched the polls, so you can give your response in the polling section. I have received one response. I'm waiting for others. Okay, let's try to see together that following helps to achieve directional solidification. So these are the some terminologies which are listed in the question, like chills, mold, chills, riser, core prints, padding, chaplets. Hello, hello, Ponuswamy sir. Can you mute yourself?
Yes, sir. Yes. Sorry.
Okay, sir.
Sorry, please,
Okay,
sir.
sir.
I've got some disturbance.
Okay. Still, you are unmuted, sir. Can you please mute your? Okay. Thank you. Okay. Uh, so and there are some casting terminologies which are given here, like chills, mold, riser, core prints, padding, and chaplets. So uh, these are the some casting terminology, but we have to see which are useful to achieve the directional solidification. So let's see what is a directional solidification. Solidification that occurs from farthest end of the casting and it moves towards the riser or the ingate. So uh, as we seen in the previous question, that always we want the solidification should happen from the rarest corner of the cavity, and end, it should end near the riser or the ingate, because they can supply they can supply continuously the molten metal to compensate the shrinkage. So that is called directional solidification. So there is a term called hot spots. So in any casting, so depending upon its geometry, it has some hot spots. So what are the hot spots? So they are the reason, basically they are the reason where the solidification happens in the very last, or solidification happens at the end. So those reasons are called the hot spots. And if you don't take care of the hot spot, then there is a possibility of forming shrinkage or porosity or the cavity. So that's why the hot spot is very important. So here I have shown pictorially some examples of the hot spot. So if you see the left figure, for this geometry, this is the reason of the hot spot, because when the molten metal filled inside the whole cavity, then what happens? Then uh, then the regions which were near the mold walls, they start solidifying quickly, because mold walls starts extracting the heat from the molten metal. So the regions which were near the mold walls, there the solidification process starts quickly, but which are the region which are far away from the mold walls, there uh, there the solidification happens later. And as per the definition, the region which is last to cool, it is a hotspot. So this is for here, this is the hotspot. So these are the region which are last to cool for the given geometry. For similarly, if we say right side figure, this is the region where the formation of hotspot has happened. And now we try to we try to address the issue of the hotspot or the problems which can happen uh, because of uh, because of not taking care of hotspot location in the casting. Those are the shrinkage, porosity, or the cavity. Why this will happen? So I will uh, show it by the example. Like this is the region where it is filled by the molten metal, and as soon as the molten metal is poured inside the cavity, then it it will get start solidifying by transferring the heat, and this region will solidify first, then this, and at last this region will be left. And when this region will solidify, then shrinkage process will happen. And if we during this shrinkage, if we cannot able to supply the required amount of molten metal to this hotspot region, then definitely because of shrinkage there will be the formation of crack or hot tearing will happen. So this will cause a defect to the casting. So we have to take care of that. So what is strategy? We will try to make a riser near the region of the hotspot. So we always, our effort is always in such a way that we should keep the riser very near to the region of the hotspot, like in this example which is figure shown in the right. Here we have, this is the riser and this is the hotspot. So we have kept the riser just above the hotspot, so that in the last, when for this geometry the solidification have started from here and it kept on progressing here to here, and this is the region which was left to solidify at the end, and that is the hotspot. And if we make the riser just above the hotspot, then when the shrinkage will start happening at the end of the solidification process in the hotspot region, then riser will able to supply the molten metal to hotspot region, and by doing this we can avoid the shrinkage, cavity, or the uh, porosity or the hot tearing in the casting. So casting helps to achieve the directional solidification. So first strategy is to avoid the shrinkage, cavity, or the cracks to by putting the riser at appropriate location. So in order to achieve the directional solidification, but sometimes this is not possible to achieve. Suppose if we have some geometry like this, okay, suppose we have some geometry like this, all this region is filled with sand, and this is the T-shaped region which is in the shape of the cavity, and it is filled with the molten metal. Now uh, the metals which comes in the contact of the mold wall, they will start solidifying like here, 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 here. So which are the region, all the regions which are near to the mold wall, they will start solidify. And so solidification will keeps on happening like this, and then after it will keeps on happening like this, but in between there will be a region like this, it will left out. So basically we don't have any provision to provide the riser or ingate near this region. Then how can we address the issue? So that kind of issue where it is not possible to compensate the shrinkage by putting the riser, there we need to use the chills. So what are the chills? Chills, they are basically metallic materials, or they are the heat sink. We know metals have very good conductivity, so they have tendency to transfer the heat from the hot zones to the cold zone very faster. So we know that this is the reason where the solidification will happen at the end. But if we want to quickly solidify this region, then we have to remove the heat from this zone. And the one of the good way to remove the heat from this zone is to providing the chills. Chills are nothing, they are the metallic materials, and they have very good conductivity. So what they will do, they will extract heat from here to here, here to here, and they will throw it out, throw it away from the hotspot zone. So if we put chills there, then this region will not become hotspot. This will also solidify with all other materials together. So by applying chills, we can avoid the formation of the hot spot zones, and that's how we can achieve the directional solidification. So there are only two ways. One is the location of the riser, another one is by putting chills. There are only two ways through which we can achieve the directional solidification. So let's start looking at the options. First one is the chills and mold. No. So second option. So chills and risers, these are the only things which can help to achieve the directional solidification. So this one is the correct answer. So if any of you have doubt, we can stay here, or let's move to the last question of the day. Okay, then let's move to the last question. So this question is all about the calculation of the solidification time. So using the Jouvry-Knopf's rules. So or for your reference, I can write the what was the rule. Basically it is used for the calculation of solidification time. So TS is the solidification time in minutes. Solidification time of anything, it may be the casting, it may be the riser, or anything, it will be equals to C multiplied by V into V upon A, where V is the volume of the casting region and A is the surface area of the casting region. If we are calculating for riser, then V will be the volume of the riser, and A will be the surface area of the riser, and C is the mold constant, V is the volume of casting, A is the surface area of casting or riser, also here casting or riser or riser. So whichever reason we are calculating, we will use those values. To the power n. N is the another constant. It's the constant. So mold constant depends on the uh, material properties of the molten material, as well as the uh, conductivity of the mold. So physical and the thermal properties of the mold and the molten material. So this depends. So mold constant depends on those parameters. So if we want to calculate so how much time it will be needed to solidify some casting resin, then we have to use this formula. Most of the time n will equals to 2. So the final formula will becomes solidification time in minutes is equals to C into V by A whole square. So this is the formula, and what is being asked in the question, suppose we have the molten cubical casting solidified in 6 minutes. Suppose when we have a cubical shape casting, and for this it requires, let's say its dimension is A, then it takes 6 minutes to solidify this whole casting. So it is asking that for the same molten cubical casting, we have to find out the solidification time for the same molten cubical casting, which is 27 times heavier than that of original. Basically, we have some bigger cubical casting of the same material, which let's say its dimension, its edge length is B, but what information we have, that this bigger one is 27 times heavier than the smaller one. So what will be the solidification time for this big one? We know the solidification time for the smaller one, which is 6 minutes, and we have to calculate what is the solidification time for this bigger cubical block, which is 27 times heavier than the smaller one, and the material is same. So please try to understand the question and try to solve it by your own. Meanwhile, I will create the polls, and please try to give your response in the polling section, and after that we will discuss it together how to solve it if you face difficulty in solving it. Then please 1 or 2 minutes to solve it by yourself, and after that we will solve it together. I am creating the polls. You can give your response in the polling section. I have launched the polls. Please calculate it, and they will and then try to give your answer in polling section. After that we will solve it together. If you are facing difficulty to understand the question, you can ask me. Okay, till now I haven't received any response, so it may be because of some numerical calculations. Okay, but still let's try to solve it together. Later on you can verify your answer with the solution which I am providing. Okay, let's start discussing it together. So uh, as per the formula, what are the information which we need? So we know solidification time for the smaller one. Let's say it is already given that the smaller one will solidify in 6 minutes. So ts for a smaller one, here for a smaller one, ts is given is equal to 6 minutes. But what is the volume? Since it's cuboidal in shape, and we know volume of cuboid is the cube of its side. Here side length is a, so the volume equals to a cube. And what is the area? So it's cuboidal shape, and we know that the area of cuboidal shape is 6a square. So basically it has 6 sides, and area of each side is a square, and so total surface area for all 6 sides will be the 6a square. But what else we need? C, but C is not given. So let's take C as C itself, and we try to put all the values in this equation. So Ts is 6 equals to C. Now V is the A cube upon area is the 6a square whole to the raised to the power 2, or we could simplify it. 6 is equal to C A by 6 to the whole square. So this is the value which we have, this is the equation which we have got, where we don't know C and we have assumed the length of side was A. But now let's try to write down the same type of equation for the bigger one. But what information we have? We know that the weight of bigger one is 27 times of smaller one. So what is the weight? Weight is nothing, is equals to volume times density times gravity. So here material is the same, so this density of the material of the smaller as well as the larger casting will be the same, and gravity is constant. So but the so we can directly say the volume weight is directly proportional to the volume, because for the both materials the density is the same and gravity is the same. So only thing which is changing is the volume of the both casting, and we can directly say if the weight of bigger one is 27 times the weight of a smaller one, then the volume of bigger casting will be 27 times of the volumes of the smaller one. So we can say V of bigger is equals to 27 times of V smaller, or what will the volume of bigger cube is, because its side length we have assumed is B, then the volume of bigger one will be the B cube is equals to 27 times the volume. What was the volume of a smaller one? It's A cube. Then if we take cube root to the both sides, then what we will get? We will get B is equals to 3 times of A. So we have got the another relation, that the side length of bigger cube is 3 times the length of the side of smaller cube. Now let's try to calculate solidification time for bigger block. So again we will use this equation. This time we don't know the solidification time, so for bigger one, let's say we can write Ts for bigger equals to C. C will be the same for the both casting, because material the material and the mold properties are the same. So C will be the same multiplied by the volume upon area. We have got this ratio as p cube by 6p square times whole square. So here we are calculating the time of solidification for the bigger casting, and we have put all the values whatever we know. So what we will get, Ts of bigger is equals to C times B by 6 to the whole square. Now we know B equals to 3A. So Ts for bigger is equals to C times 3A by 6 to the whole square, or what I can write, Ts of bigger is equals to 3 times of squares. I bring out the 3 square out of this parenthesis, then what we are left with, 3c multiplied by a by 6 to the whole square. Now what is this? This is nothing, this is the same. So the value of this thing is 6 here. Okay, then we can write solidification time of bigger block will be 3 squares time of this whole value is nothing but it is 6. So it will comes out 3 square is equals to 9 multiplied by 6, it will be 54, and it will be in minutes. So the final answer or the solidification time of bigger block will be the 54 minutes. So the correct answer is 54 minutes. So I think I have explained the solution, but any of you have found any difficulty to understand any of his steps, then please unmute yourself and please ask me now. Okay, so I think all of you have understood all the steps which we have followed to solve this question. So if it's clear to everyone, then we can stop this session here. So I think I was able to explain all the questions in today's session. So if any of you have any feedback, please unmute yourself. Please let me know so that we could improve this session by next weekend and onwards. Or if it's okay, then we can end this session here. You can write in your chat box.
Thank you, sir.
Okay.
We can able to understand your explanations for each and every question.
Okay.
So that we can understand very well.
Okay, sir.
Thank you, sir.
Thank you so much, sir. So wish you all the very best.
Thank you,
Wish
sir.
you all
Thank
the
you.
Janmashtami, as well as wish you all very good weekend. So let's meet in the next week with some of the questions which are related to the lectures of the 5th week. So okay, thank you all. Let's end the session here. Thank you very much.